Ready to go to work?
I believe so, yes.
Excellent. So our next speaker is James Wheeler from Bristol, who will speak about Mobius hyperbolae. And please go ahead.
So yeah, I'll start. Thank you for the opportunity to talk. And yes, I'll be talking about some incidence bounds with hyperbola. So these is all based on my joint paper with my supervisor, Misha Rudnev. And so in the talk, we'll sort of go through the background, what has been previously done, what our setup is, and the like, before sort of going through our results, which I've spread out over a few theorems just because it's fairly complicated if you put it in one big lump. We will then try and look at the proof outline. So I'm not going to try and prove these theorems in our 25 minutes because that would be incredibly difficult at the times, but we'll have a look at like the major points, where they've come from, what tools we're using. In particular, this will be in the form of an intermediate theorem, which we use, and some energy bounds, which we will talk about. And these energy bounds come in like a standard T2 energy. We talked a bit about higher energies earlier in the conference, but I will go through that again. And we've also got this T3 energy, which is a higher energy. And this has an interesting link to the Minkowski distances. And if we've got time at the end, we've got a couple of corollaries I can show, sort of one to do with we will sort of work towards sort of the Erdős unit distance problem in sort of in this setting, and some product style results. So yes, our setup. So we're looking at incidence bounds. So so like the famous incident bound is going to be semi-ready trough. So this is for points and lines rather than our points and hyperbola, and that for a set of P points and a set of L lines gives the sort of we're probably fairly standard in accepting this of the semi-ready trough theorem. So we want to do a sort of similar thing with this, but having replaced our lines with hyperbola. We'll be working in a field, predominantly a finite field of characteristic P. We'll have a quick comment that sort of result can work in the reals if we swap out our intermediate theorem with a theorem of Sharia and Solomon. We will have a subset of our field A, which will be our point set, sort of A times A. And so these are the points we were taking the intersections with. And for our main result, we're going to be looking at a set of hyperbola, which are translates of this xy equal -1 hyperbola. We can replace this -1 with other constants if we need to. Sort of keeping it simple in this talk, -1 is as good as a good term. It makes the calculations look good. We will also sometimes be thinking of these hyperbola as Mobius transformations. That allows us to use various other tools. And we will also sometimes consider them as we translate AB. So this is like a 2-parameter family. So we consider these as sort of almost points in some cases if we want to. And finally, at the bottom, we're using this sort of sigma notation, so sigma A of H. This is just the number of incidences between our point set A times A and our hyperbola H. And so we can see we can write this as a sum should we desire. So like if we put a point of A into our transformation, we get a 1 if we get a point in of set A out, and we don't add anything otherwise. So cool. Anyway, so before we get on to my results, we'll have a look at what people have previously done in the area. So the first of two results which you're going to look at really, which are the majority of these hyperbola aren't quite as popular as our point and line instances, is this theorem due to Bourgain. Few differences from our setup is that this works for a 3-parameter family of hyperbola rather than just our translates. And its proof is sort of based on a series of repeated Cauchy-Schwarz and the use of like the L2 smoothing of Bourgain and Gambit, and comparing this to Helfgott's growth in SL2. And so this gives us a slight improvement on the absolute, the trivial we can get is A times H. So Bourgain here has got this improved by a delta, which is some small constant. They've got some conditions about not being too caught up in subgroups. But this is just sort of get rid of sort of awkward cases. I think we could reduce this restriction slightly with arguments from Treatise and some others using energy, but I will leave that to someone else. The other main theorem sort of in this direction, and I suppose the theorem which we have taken in our paper was our aim was to try and generalize this a bit, is due to Skredoff. In his paper, it's a bit more general. We've sort of taken, instead of just having A times B for hyperbola and such, we've simplified it down to here to so easier to state. But the main point is we're back to our two-parameter translates for hyperbola, but Skredoff has his hyperbola in a Cartesian product, and like one of our big goals is we would quite like to get rid of this restriction on the hyperbola, and that's what we will do with our theorems. I also sort of point out we've got in the minimum we have these two lines. So the first one is coming from the T2 energy, and the second comes from the higher T3 energy. So when I come to state my theorem next, I will sort of do these on separate slides, but if you could consider them keeping them the same way of having a minimum like we've done here. So moving on to sort of like I'll try and generalize it. So for the first theorem of myself and Misha, we have this bound. So this is the T2 bound. So this is predominantly works for hyperbola, which is this better for sort of a lot of our cases. We can deal with when our set A is quite large with respect to P, the characteristic P. We're using, but I've not put this in here just to try and keep the talk fairly simple and straightforward and going along. We have a similar estimate if we use the T3 energy, which is slightly more complicated and is better in certain circumstances, but sort of when we have richer hyperbola. So that is hyperbola which insert a lot of points, we tend to do better. This is because as we increase our energy, our result starts to pay attention to richer and richer hyperbola. This is also why, unlike Bourgain, we can't just keep doing our Cauchy-Schwarz and get us again and again getting improvements, because we end up just working on richer and richer and richer hyperbola, which is eventually this stops being of use. I also said that we can say something about the real case. So this is using the result of Solomon and Schreier rather than our intermediate theorem. It sort of gives us another bound, which can be of interest to those people who prefer working in the reals rather than say the finite fields. So having sort of stated our theorem, what we want, I will sort of go for an outline of our proof. So with most combinatorics, like with most combinatorics, once we've sort of written it as a sum, actually I should say that this follows some of the ideas from Skredoff's proof, but we're sort of acting to try and improve on it to get rid of the Cartesian case, and we use this intermediate theorem, which is new. But yeah, so as with a lot of combinatorics, once we have our set of a sum, we can use Cauchy-Schwarz to split it up. So after a couple iterations of Cauchy-Schwarz, we have got our incidence split up. So we have our energy part here, which we will use and deal with our energy bounds. And we have this second part, which we'll use with our intermediate theorem. We have an undefined so far omega here. So omega we should see as a set of rich Mobius hyperbola in H times H inverse, and we have gained this via pigeonholing. But so without going into videos exactly where it comes from, we can see this as just, we'll deal with this with our intermediate theorem, and we'll do with the energy with our energy bounds. Instead of stopping now, we could have gone, I mean, we could keep going for as long as we want, but we could go for at least one more Cauchy Schwarz. And here we'll be instead to get a higher energy, and we've still got intermediate. So this is how we get to our second idea and use, but this will use a higher energy term. We in fact use T3 because it is slightly easier to calculate than T4, and we just make use of the that if we have T to the K of AOS, we have an easy bound of sort of H. Of H, so we could use this bound to sort of reduce from our T to the 4 down, our T4 energy down to our T3 energy when we come to that. So hopefully that's sort of given you a vague idea of why we want our both energy bounds and our intermediate theorem. So I suppose the next obvious question is, what is our intermediate theorem? So this is another incidence bound, which is slightly more general. This is not just for the translates, but for more general Mobius hyperbola. And you can see here, I've left it in the cases that when we've got various sizes of A in comparison to our characteristic. So we can do similarly we can deal with these higher like large A and H sets in our first theorem, but we've left out for legibility. In particular, though, in a small A case, we have the maximum number of these K-rich Mobius hyperbolas is A to the 7 over K to the 5, and this is sort of the important use. And as I pointed out earlier, for the reals, we can instead use this result from Solomon and Sharia, who have that the maximum number of K-rich Mobius hyperbola is this instead. So we would plug that in, and that's how we get the real case out. Considering the proof, or the proof ideas for this intermediate theorem, we consider the subset of our hyperbola, which incident to our, say, favourite point Q. We can then apply a transform, which I find is quite interesting, that we can take our Mobius transform sort of hyperbola and transform them into affine lines. And then having done our transform, we similarly transform our point set A times A, so that the number of incidences between our hyperbola and the point set is now equal to those between affine lines and a point set, which is more commonly understood. And so here we then make use of the Sophie Stevens and Frank Dezou's point line incidence theorem to get back to our theorem. So that gives you a quick idea of where the intermediate theorem comes from and how that's proven. What remains is then the energy bounds. So these higher energies have been talked about a bit earlier in this conference, but I will restate here what we have. So we've got our more standard energy, which will sometimes write E of H, I'll sometimes use T2 of H. And this is pretty much what you would expect from an energy if you've seen them before, and our operation is just a composition of these transforms. These higher energies, instead of having 2 on each side, we can just go to 3, and we keep oscillating between the H1, H2 inverse, H3, H4 inverse, and so on, if we were to define higher, or T4, T5, as high as we want. The use of the inverses is just to deal with the fact that we're in a non-commutative setting, which can sometimes cause some issues. Otherwise, having sort of got what I mean by our energy of these hyperbola, we'll look now at the 2 energy bounds. So we'll consider the T2 energy first, because that is the simpler of the energy. So this gives us our nice lemma, that our energy is restricted by the square of the size of the hyperbola and this m, which is sort of to do with when we're considering our hyperbola as sort of being corresponding to this AB, which is their translation, we don't want too many of them in one line effectively. If they're all in a single line, things can become, we can get problems. If you're in the Cartesian case, then this M is sort of square root of H, which gives us a sort of a nice expected bound. And we sort of note that this M can sort of vary between the square root of H up to, well, I think it can vary between, I suppose it can vary between 1 and H, which gives us our what you expect bounds for normal energy to be of between the square and the cube. Way we get around to proving this is we can represent our hyperbola by an SL2 matrix as given here. We can then calculate effectively this H1, H2 inverse is equal to H1 prime, H2 prime inverse. And we can then effectively consider the 4 equations we get by considering each of the sort of the entries in our matrices. And after some rearranging and simplification, we get to the fact that they are hyperbola satisfy this equation if they satisfy one of these 2 systems of equations, where the hyperbola H1 is the translation by A1, B1, and similarly with the primes, when we want to consider said prime. And so for those of you who can look at this, and we can sort of see that what this are saying is that if we have these 4 hyperbola satisfying this, they're effectively in some sort of parallelogram shape with sort of because the A1s and A1 prime on one, the A2 and A2 prime on the others, and then we've got our B1 minus B2 as the distance is the same, and we need to find a similar distance on the other line, and then what we are left is counting these parallelograms, which is what this H squared M comes from. So I think that gives us our there we go. So that gives us our T2 lemma. T3 lemma looks a bit more intimidating, but rather than really, so this is what the end result is. Really, the energy side result is more to do with this here, where we have this H4 comes from sort of dealing with some sort of trivial bounds of things being stuck in Borel subgroup. But it is this Q of H which is particularly interesting. So in the literature, this is sometimes referred to as sort of rectangular quadruples. And we can sort of see this as, in some ways, if we have H1 and H2, these rectangular quadruples are considering ones which have this area of this rectangle where the edges are parallel to the axes, and we are considering sort of H1 prime having the same rectangular area as this for H2 prime, which is a fairly interesting quantity which you may or may not expect to come up. Or at least not yet. I'll sort of make it clear why we expect this to come up in the following slide, which is where we sort of bring in this understanding of the Minkowski distances. So we can apply a transformation, and then instead of having this rectangular areas be equal, we have the Minkowski distance being equal. So this is sort of like distance equations. So I should probably introduce exactly what we mean by the Minkowski distance. So we are probably familiar with the Euclidean distance. We have this sort of x squared plus y squared, and this is our distance on our quadratic form. For the Minkowski distance, we instead have, we're considering the quadratic form x squared minus y squared. I mean, I think this originally came up when Minkowski was working with Einstein on relativity. So you had like your space-like x's and your time-like y's to come up. But for us, so for us though, what I find particularly interesting is if we consider like sets of equal distance from the origin, say for simplicity. In the Euclidean, this is of course circles. are like circles of equal distance. However, for the Minkowski distance, our sort of equal distance sets are hyperbola. So considering we are dealing with the intersections of hyperbola, this could be a good reason for sort of intuition of why we've come across this as a object. I will also point out that if as we're dealing with this, we're not quite in a proper metric, because we can have points which are distant 0 apart, but definitely different points. So we have to deal with these sort of so-called isotropic distances separately, but these sort of get subsumed. So like this does not turn out to be much of a problem in the long term. But it is something you have to pay attention to and care about. The other point which is worth making here is if -1 is a square in our field, which it can quite easily be, then the Euclidean and the Minkowski distances become the same thing, because we can change our x squared minus y squared. We change this to our x squared plus iy prime squared, and we've gone from our Minkowski to our from our Euclidean, from our Minkowski to an Euclidean. So having sort of introduced where we get the Minkowski distance, like for the cubes, how we actually gain such a point is in the same way we dealt with in our T2 theorem. We now consider this H1, H2 inverse H3, and we equate them. I'm not going into the detail, but like this is a slide as much shows that as we get to higher and higher energies, the complexity of these equations grows quickly. And this is one of our main reasons we didn't really want to deal with T4 in and of itself, because that would be even more complicated than we are here. This is fairly complicated as is. So, having made that comment, having sort of using these Minkowski distances, we've now got these sort of, the cube we want sort of bound is the number of solutions of distances, and we can make use of a theorem from sort of Murphy, Petridis, Pham, Rudnev, and Stevens, which gives us this way of bounding our Q. So we use this, we plug it in, and we can see that this is where our lemma comes from. We've got the same points in. So that gives the basic ideas behind our proof, while skipping over all of the details. So having done that, I will use our sort of last few minutes to sort of talk about some of our corollaries which we've come up with. So the first one is this sort of realizations of Minkowski distance, and this is sort of, in some ways, would be a nice step towards trying to get the Erdos unit distance problem. We run into some issues because there are some bad examples where, due to wanting to try and rotate, this breaks our Cartesian setup for our points, because although we've got rid of the Cartesian requirement for our hyperbola, the Cartesian product for the points is fairly baked into how our proof works. But if we could get it to work, this would be interesting, because it would our a to the 29 over 10, but that's sort of beating the sort of the size of the point set to the 3/2, which is sort of the equivalent of a cubed, which is the sort of standard trivial, and is also what is sort of expected. I think Zal proved that we can reach in 3 dimensions rather than in this 2-dimensional case, and with a few other conditions that we actually reach this 3 over 2 and you can't do better. So it could be that we can't do better than this, and it's just in these specific cases where we can. The second corollary, it just is giving some product style results, which more or less come out of our proof on their own. But I've not got uses for these as of yet, but some product results can be of use, and maybe we can find applications for these, which would be nice. And I think that is pretty much what I was planning to talk about. So I will thank you for listening, and I've actually managed my time fairly effectively for this time. Yeah.
Thank you very much, James. If you look at the Q&A, you will see that Sophie Stevens has a question for you.
Yes. The main theorem is typed in some cases. I mean, in particular, not the bits which we were showing, but with when A and H are large with respect to P. But this is as much because we are making use of the other various bounds which are tight and they just sort of follow through. I don't know what the conjectured upper bounds should be for this. So I think the other problem is that it could be in some cases, but then you sort of trying to deal with which cases should be treated as trivial cases to be ignored, sort of dealt with separately, and which ones are actually interesting cases. And I suspect that that's probably as much of a question in its own right as in of these. I remember trying to working out exactly which cases were tight, but I've not got that to hand now. I don't think I'm trying to remember or give the correct answer. So I can talk about that more at another time once I've looked up the answers again. I think it's probably safest. Was that the only one for questions?
I believe so.
Oh, okay.
So thank you very much, James. And the next talk will be